Okay. So welcome to the after tea session. So this particular lecture will be continuation of what we have already been taught in the first 2 days. So we have taught you the optimization of a molecule in the frequency calculation and then the periodic DFT method. But what we will do in this particular lecture is we will see how we can calculate the solvation calculation. How we calculate the solvation calculation. What do you mean by solvation? We will see. So we will be taking up the first a model called as Cosmo, that is conductor like screening model. Q stands for conductor, S stands for screening, MO stands for model, Cosmo. That is the point. So that Cosmo file it can be used from the scratch, from very molecular level, and then finally to the macro level. So it can be also used in processing different packages such as Aspen. So those who are in chemical engineering, they must be aware of what Aspen does. So that's what it is. So because if you don't have a molecule in your hand in Aspen, you cannot move ahead. So one way of including a molecule in Aspen is you do a Cosmo calculation and then input a certain thing that is sigma profiles into the particular simulator. So we will see first what is a model of. So I will skip some part of it, geometry optimization. This process. So I'm not going through this. Hopefully, you know all this. X I is equal to E psi. What is our Schrodinger? The same theory behind it, whatever Dr. Ali has taught in the first day. Okay, so it solves this equation, Schrodinger equation. So that is a psi, that is a wave function of where the probable particular electron is. Hamiltonian, you know, it is all the particular operators clubbed together. The operators act on this wave function to give the eigenvalue and the wave function. So I'm just going. This is time dependent Schrodinger equation. So I'm just skipping these slides now because this has been already taught. And this is Born-Oppenheimer approximation. You must be knowing this separation of nuclear and the electronic motion. So if you can separate the wave function of nucleus and the electron, you can compute the wave function and calculation easily. So these are the two chemists who have provided this expression. And this is, you know, the molecular orbital, linear combination of molecular orbital using the basis function. Yes. So I'm not going into details. Okay, this you have know this mathematics. They can skip this. So this is overall Hamiltonian consists of the kinetic energy, nuclear attraction energy, Coulomb operator, and the exchange operator. Special type orbitals is already been taught. Gaussian type orbitals, because we are working on Gaussian. So that's why we are using Gaussian type orbitals. So the Gaussian type orbitals are of this form. Okay, some this x to the power of a, y to the power of b, and z to the power of c. So there are certain functions relates to a plus b plus c equal to 0. So you have a s-type Gaussian. Then if it is 1, we have a p-type Gaussian. So it has px, py, pz orbital. And if it is 2, like that, we have p-type orbitals. And then we also, and this particular parameter controls the width of the orbital. So large values of this gives kite function and small values of this give diffuse function. And then we have the split valence basis set, that is 431G. So the valence sets, these are splitted 3 and 3:1, inner core and outer core, and this orbitals. So it means the nomenclature 431G implies it has 4 Gaussian functions. Inner valence orbitals have 3 Gaussian functions, and outer valence orbitals have 1 Gaussian. So G implies it's a Gaussian function, capital G. So we'll be using this particular basis set. So I just give this actually. So this has been already taught. So the starting point for a good this quantum chemical computation. So it's a structural changes within a molecule produces differences in its energy and other properties. So this already have been taught. The potential energy scan, all this by Dr. Ali. So not going into details. So Gaussian 09, you know, is the most popular quantum chemistry packages. So this you are aware. So it is our input file consists of a root section where you write the keywords, root section. Then you write about the molecular charge and multiplicity, and then some definition regarding the molecular structure. So all this information is used to calculate the total number of electrons and its orbital occupancy. So this is the earliest way which we wrote actually the sample input file. The root section is this, then your title section. Then you have the charge here. This is the charge, overall charge of water. This is the multiplicity, which is number of unpaired electrons plus 1. It becomes, there is no unpaired electron, so it is 1 for water. And this is the way you write the Z matrix. So you have oxygen at the first atom, hydrogen at the second atom. So the second atom is connected to the first atom, that is 1, with a distance of r. That's what it says. And the third atom is connected to the first atom, the distance r, and then making an angle with atom 2, this one, with the angle A. That's what it means. And the distances and angle are written here. This is the distance, the angle. So the root section has the type of calculation. You can write the job type, which is you are doing want to do optimization or a frequency calculation, or the method you want to apply Hartree for can be this MP2 or MP3 type of calculation, then DFT calculation, then the basis set. The charge is the overall charge of the system. Multiplicity is the measure of the number of unpaired electrons in the system. So the thumb rule is number of unpaired electrons plus 1. Now, dihedral angle, I hope everybody has understood. If not, you can see this. So it consists a type of based on the geometric position. So if there are 4 atoms, first 3 atoms will make a plane, and the last 3 atoms will make a plane. What is the angle between these 2 planes? That is the dihedral angle. So this is first atom, second atom connected. This is the one. This is one plane. This is the 4th atom. So this 4th atom you can put anywhere, here, anywhere. So how do you constrain it? So that's why you require this dihedral. So this is one plane. This is other plane. The angle between these 2 planes. That is the way you constrain the 4th atom. It can be here also. Earlier it was up, now here. So it will be, what is the angle now? 180. Okay, between the 2 planes. That's how we actually write the dihedral angles. And dihedral angles you have seen both in Monte Carlo and all this, you have to mention these dihedral angles. So because wherever the 4th atom comes, you have to specify that by a dihedral angle. So this is the normal optimization flow sheet. You write a Z matrix, multiplicity, all these, submit the job, try with a smaller basis set. If it is converged, do a frequency optimization, frequency calculation, and check all these are positive. If it is positive, you stop. If it is not, then you have to go back and see where is the error. So you have to resubmit the job. So check error if the multiplicity is consistent, if bond angle is between 180 or basis set is correct. All this you have to check. So these are the 4 criteria Gaussian uses to stop a calculation. So you get at the end you will get a quote. You will get a quote in a Gaussian log file. So that quote will come only when this finally the job terminates normally and these 4 conditions are met. Forces must be essentially 0. Specifically, the maximum component of the force must be below the cutoff of this value. The root mean square of the forces should be 0 or below the defined tolerance of this value, or the calculated displacement of the next step must be smaller than the defined cutoff value, the root mean square displacement. So you have first the forces, root mean square force, displacement, root mean square. All these 4 should be within this convergence criteria. Then there is a normal termination in the Gaussian program. So this is nature of stationary points. A structure which has n imaginary frequency is an nth order saddle point. So 0 imaginary frequency, the structure is the minimum, else the structure is a saddle point. So now we come to the continuous solution model, because this is where we are going to apply the Cosmo model. This was just the basic what I discussed. You know this So this is the model all about. So what you do is you have a solute. Suppose you have a solute. You had a model prior to this also. That was called the polarizable continuum model. So what it is, if I put a solute in the midst of a solvent, how its charge gets polarized, how the interfacial charge gets distributed. So that you will find the different, you can find the what is the charge distribution of the solute when it is placed in a solvent. So solvation phenomenon is thus defined. If you want to actually define this in terms of steps, it is formulated by defining a cavity. Suppose you have a solvent, you define a cavity. So you have to put a solvent. So you have a solvent, you put a solute. So if you want to put a solute, you need to define a cavity in which the molecule will be inserted. So in the midst of a dielectric medium. So you don't write the solvent explicitly. You specify what is the dielectric constant of that medium. So you know the dielectric constant, you specify, and then you put the solute inside the dielectric medium. So solvent distribution outside solute is assumed to be constant. In continuum solvation models, what you do is you assume that it is constant. There will be a constant solvent. So solvent charge beside this solute is all constant. So it means this will lead to the solvation free energy. The solvation free energy means what is the amount of energy I require to place the solute in the midst of a solvent. How much energy do I require to place a solute in the midst of a solvent? That is the energy belonging to three parts. One is the electrostatic contribution due to the charges. Next is the van der Waals because of the shape and size. And the cavity term. Cavity term means the energy required to produce a cavity within the solvent. So if you know these three terms, electrostatic, van der Waals, and cavity, you can calculate delta G of solvation. So this delta G of solvation is very important because this has direct relevance to a chemical potential. Those from chemical engineering background will come to know because this delta G solvation you can relate to activity coefficients. That's what the entire purpose is. So if I can use this continuum solvation model and calculate this particular expression, then I can have a route to calculate activity coefficient. So first, let us see these terms. So it is clear to you. Any question you can ask? These three terms. So, but there were other models also. Polarizable continuum model already there. Then why do we need another model? So there are. I will come to that. What is the disadvantage is for that polarizable continuum model and this model. So PCM or polarizable continuum model was defined earlier. Tommaso and Persico gave this model. So how does this model differs from this model? It differs in the way the solute is described, in the way the solute charge distribution is described, and the interaction of the direction. So it will solve because if you place a solute in the solvent, in the interface charges will decide. So now how do you want to calculate the charges at the interface? So what it does, this PCM type models, it use exact boundary condition related to the dielectric constant. Exact boundary condition. But many cases, this is not possible. So we will see why it is not possible. So in this case, the polarizable continuum models or PCM models, here it implies that solvent is a polarizable continuum and a solute is placed in the cavity. That is, solute is placed in the solvent. The reaction potential is then described in terms of apparent charge distribution spread on the cavity surface. Because if you make a cavity, you place a solute in it. So on the cavity, there will be charges opposite to that of the solute. Then only it will be able to neutralize, right? So a cavity will acquire some charges, and these charges are drawn from the solvent medium. It will try to neutralize the solute charge, right? So our entire aim is to find those charge distribution, which is on the cavity, not on the solute. So tessellation means breaking. So if we can assume the solute as sphere, so can we break the sphere into small this particular this name? It means that can I make the entire sphere, break them into small tessellate? Tessellate, you understand? Small pentagons. across all the spheres. Because if you make a pentagon type of structure on the surface of the sphere, you can assume it to be circular. That was the idea. So the tessellation means the breaking up, or you may the dividing the spheres into uh, this particular shape, pentakis dodecahedron. It is a polyhedron derived from the dodecahedron by replacing each pentagonal force with 5 triangles. So let us see. Yeah. This sphere, each part is converted into one pen. Each part, it is a sphere, and on top of the surface of the sphere, the pentagons are there. Yeah, pentagons are there. So several pentagons are made. So I will show that, no, the diagram, how it looks like. So how is the cavity creation? Cavity creation term is tricky. Unfortunately, we don't have to take care of all this. This Gaussian set of programs they have, they will create the cavity based on the keyword to specify. So if you specify the keyword PCM, it will do in a certain way. If you specify the keyword Cosmo, it will do it another way. So it is one of the simplest way cavity is created is whatever you want to insert in the solvent, you just assume it to be a sphere, and then you add up all the spheres. So it's a mere union of spheres. This is called the van der Waals surface, and is sufficient to describe the continuum for molecules of small size. For small size, you can assume the van der Waals radius as the sphere radius for individual atoms. So if you have water molecule, you need to know the atomic diameter of hydrogen and oxygen. So you join them together, you will get the entire surface. Then there is a solvent accessible, because not all the surface of the sphere is accessible with the solvent. That's what the term comes here, solvent accessible surface. This is the accessible surface which is stretched out by the probe sphere as it rolls over the surface solid. Then I'll show you the diagram in the next slide. Then you will understand. So all these particular approaches, these three, Gaussian has this what they call the G-Pol algorithm inbuilt. PCM is based on this G-Pol algorithm that is generating polyhedron. I'll show you the structure. This is the 3 different structures. This is the van der Waals surface, which I just discussed. It's solvent accessible surface. It means it will trace out how this solvent probe sphere is going in this direction. That is solvent probe sphere. Then it will, and this one is actually on where it touches. So that is the solvent excluding surface. This is another surface. So you have the solvent accessible surface, solvent excluding surface, and van der Waals surface. These 3 are the ones which are being done on initiated by G-Pol algorithm. So it is performed making use of 2 nested cycles. The internal cycle calculates the final charges on the surface elements from the molecular charge distribution, and the external one determines an improved solid charge distribution. Spheres of the heavy atoms are defined taking into account their hybridization state. The radii of the sphere. How will you find out the radii of the sphere? It is found by fitting the solvation free energy over a large set of molecules, taking into account non-electrostatic contribution. Because it's on the shape and size only, so you take only the non-electrostatic contribution. So this implementation of the PCM model in Gaussian can be done by using this keyword SCRF, self-consistent reaction free. So SCRF equal to, when you write something, it is asking you to execute that algorithm. So now what is the disadvantage of PCM models? First is the electrostatic solid-solvent interactions are included in the PCM, but the calculation to solving them is very difficult because it uses exact boundary conditions in the dielectric. The results lead to conclusion that for some molecules such as cyclohexane, acetone, methanol, acetonitrile, electrostatic effects are dominant, while for compounds such as CCl4, benzene, chloroform, non-electrostatic effects are more important. So there is a biasness in the solution procedure, the PCM models. So that's why the PCM models were not much useful. So the fact is, it uses exact dielectric boundary condition. I don't want to go into the details of the mathematical calculation. So what Cosmo did was, it assumed that the entire solvent is a conductor instead of a specific dielectric constant. It assumed that the entire solvent is a conductor of infinite dielectric constant. Infinite. Okay. This is a change from PCM. PCM you have specific dielectric constant, but here you have an infinite dielectric constant so that it can screen all the solute charges. Only thing is they use a scaling factor. So this scaling factor means this inherent solute charge distribution. So you can calculate whatever charge which is coming onto the surface if you multiply this with a scaling factor. Okay, so this is the dielectric constant. So it roughly produces results of the actual scaling charges onto the cavity. So instead of solving for this exact dielectric boundary condition, it uses a scaling factor. This F epsilon is the scaling factor, and the scaling factor is given by this expression. So this was actually called the conductor-like scaling model. Cosmo. So this was pioneered, initially started by Andreas Klant. It was stands upon and it will be used for complete polarization. So it doesn't matter, there is no biasness, whether it is amines, alcohols, hydrocarbons, straight chain compounds, there is the infinite electric constant. It will spin the entire charge of that particular cell. So the segment surface created by van der Waals-like surface is determined by the union of spheres. And each element he is given here in the Cosmo model to a specific radius. This radius are called as Cosmo radii. This Cosmo radii is bigger than van der Waals. It's roughly 20% more than the van der Waals radius. So this is available for 11 elements. This is maybe more now, but this is when this was 11 elements. Probably now there are included much more elements. And this atomic radii were obtained from close to 15,000 DFT calculations. Given their extensive optimization, the commercial packages don't try to use the atomic Cosmo radii again and again. They will use this Cosmo radii directly. So the commercial packages directly use this data. So there are two parts involved. First is the conductor-like screening model, which is the quantum chemical calculation. Then when you get the screening charges, what is the charge on top of the cavity? So that charge you take up as a statistical thermodynamics input. That charge you actually relate it to a activity coefficient of chemical potential. From that charges, we will then calculate, if I know the charges on the cavity, how much amount of energy I require to put from outside to remove this charge. That brings the free energy, that is delta G. If you know delta G, you can calculate chemical potential. If you know chemical potential, you can calculate activity potential. That is the way it is calculated. Clear? You get screening charges of quantum chemical information, and this has to be done only once because these are all unimolecular calculations, single molecule. You do it once, keep it in database, and that's it. Whenever you write the program, this is this you have to write a program yourself. There are equations how to convert this screening charges into delta G, that is its free energy, difference by its free energy. Okay. So this is in Gaussian 16 is there. How to generate the Cosmo file. Only this part is there for Gaussian. Only this part, Cosmo. The RS and SAC part, you can get. So this was, he actually pioneered this Cosmo file and just clapped. And then he started this company, Cosmologic, but I think this is no more there. This is now under Dassault Systems. So he has sold this company. Initially, he started with Cosmologic. So in Cosmologic, you can do both of them. The Cosmo as well as SAC calculation. RS stands for real solvents, which was coined by Andreas Klant. SAC stands for segment activity coefficient. Now, when they were developing the model to calculate activity coefficients, so he was a physicist. So there were some inconsistencies. So that was actually solved by Standard. So when he solved that, so he named that model as SAC. So he has actually coined this term SAC. So now most of us we do with Cosmo SAC. That is the segment activity coefficient. Okay. So now it is come here. Now they sell it. This the all systems they will sell this Cosmo term package. Here you can get both Cosmo as well as SAC. Everything. You will get the activity coefficient, enthalpies, all these things you will get. So this is the way you can calculate Cosmo file. But in this particular class, I will be instructing you how to get the Cosmo. But let us see first the equations first. So now this is what we do actually, construction of molecular surface now. So as I told you, entire surface is broken into tiny polyhedra segments with its own position and area. So this is, suppose each segment can either be a pentagon or hexagon, but for computational affordability, each is assumed circular. So I told now this will be broken into a pentagon type structure, the entire here. So this is a pentagon structure, but for complexity, computational affordability, this pentagon structure is assumed to be a in circle in nature. So with the radius Rn. Okay, any question? So I'm breaking the entire solute surface in terms of these spheres. So suppose this is the atom of hydrogen. Atom of hydrogen has this much surface. This is a three-dimensional image. So I am breaking them into small pentagons, each with their own radius. That's what I'm doing. That. So I have to do it for all the atoms. So what are we doing then? What are the steps? The molecule is immersed in a homogeneous conductor having infinite dielectric constant. The screening charges from the conductor. So there will be charges from the conductor will try to cancel the charges of the solute. If you try to cancel, you have one side you have solute charge, another side you have the conductor charge. They all coming together and they will stay and they will meet at the interface. This is physically modeled by placing a screening charge from the conductor on each segment. So it means once you have made those segments, on each segment there will be some charge. Then only it will be cancelling out. So the charge will be opposite to that of the charge of solute. Suppose hydrogen, we know it is positively charged in water. So negative charge will reside on the surface to cancel out that charge. And what is this negative charge? That is what we will be calculating in the Cosmo calculation. So this total energy of solvation. Now, what is the total energy I need to place it in the cavity? So, what type of interaction do you think there will be? You take a solute, immerse it in the conductor. First, what sort of interaction? First is the screening charges with the solute nuclei. Nuclei will interact with the screening charges. Then the electron density, the screening charges with the solute electron density. So electrons will interact with the screening charges on the surface. Then the nuclei will also interact between the screening surface or between the screening charges. And then there will be interaction between itself, the screening charges within itself. So the screening charges within itself, there will be one interaction. The screening charges have interaction with the nuclei, and the screening charges will have interaction with the solute electron density. Three things. Here, three things. Within itself, with nuclei, and with the solute electron density. So these three we have some mathematical equation. So what are the different steps then? Let's go. Step one, we optimize the molecule. So this optimization is same what has been taught in the first day of the workshop. Just optimize it. Then you construct a segmented surface. This is the segmented surface. A different pentagon. Radius of each sphere is specific to the element to which atoms belong. So the overall, this is, let's say, hydrogen atom. It has a radius which is optimized. We don't do it again. That is 20% more than the van der Waals radius. Within this sphere, these are the different segments. This is one segment, two segment, like that. Radius of each sphere is specific, and division into tiny polyhedra with its own position area. So all this polyhedra may not be same in size. They will be different in size. but each segment is assumed to be circular because it simplifies the calculation. So this is the expression what Gaussian does. So Gaussian, it will try to find out E solve. So energy of solvation solves the interaction of the segments with the solute nuclei. So this is that term. A here is the different nuclei. Z is nuclei number, different nuclei. Q is the spinning charge, which is on the surface. This is some constant. Then the second is with the solute electron density. This one, with the solute electron density. This particular term is the solute electron density. So C alpha is a parameter which actually says what is the electron density of the inherent question. And Q alpha is a spinning charge. And then what is the interaction between the two adjacent segments with the charges Q alpha and Q beta? Clear? So this is with nuclei, this is with solute electron density, this is within themselves. So these are some expressions you don't need to worry. So as I told you, C alpha, what is this C alpha? It is the integral V alpha. V alpha is the electric, it's a electric field of the solute. So function of the electric field multiplied by the electron density. So this is here. Okay, so it's written here. B, C, D, R represent vector quantity, represent the contribution due to Coulomb's law. Z alpha, R alpha denotes the molecular charge and position of nucleus. So Z alpha and R alpha. So here you have the R alpha. Ra is the position of the nuclei. So it is the difference of the distance. Then there is a term called D alpha alpha, because here there will be some term which is called alpha becomes equal to beta. So it will be alpha and alpha. What is that is called the self energy of a segment. It is the represents the energy required to provide a charge on each segment. Is it clear? This is what it will calculate this question. It will apply this expression. Now, if you want to solve this expression, you need to do a derivative of this E solve. Derivative. So this self energy, I don't not to worry. The expression is so this you can the expression for the self energy was made by assuming the molecule the sphere of radius r. The total charge Q is distributed homogeneously. I think you can just skip this expression. It's not much. But only thing you remember, we have these three expressions. This is only for the self energy term. I'm like, you can skip for the time. So, yeah. So, I mean, you can go through this. It's fine. It's only these expressions are used to compute the final expression for the self energy term, because we have a self energy term Q alpha into Q alpha. That is that final expression. So don't work too much. Finally, what we are having is this expression. You remember E solve equal to, you have three terms. This one term, nuclei term, then you have this solute electron density term, and this is this term, what you call it within itself, the charges within itself. So now we have what Gaussian does, it will solve this expression. So you do a derivative with respect to the scaling term. Now, to solve this, because you need to minimize this. If you want to solve this expression, you need to minimize this. So you will get a solution where Q alpha is converged, and that particular Q alpha will be printed in your Cosmo. So scaling charges causes the electron density to polarize. So if you suppose you put a different scaling charge, you will have different. So it's a trial and error approach. You solve this expression. So at each step, scaling charge is found for the current electron density, after which it is updated for a new electron density. So yesterday there was 2 days back there was a question, what is SCF calculation? This is the SCF calculation. So you just at each step, the scaling charge is found for the electron density. If it does not match, it is again updated. They keep on doing this until you solve for this expression. This entire procedure, in this case, SCF is called the Cosmo calculation. So in the Cosmo calculation, you are finding this spinning charge. So in addition to charge and area of each segment, it also provides the potential for each segment as well as the total energy. So it will provide for each segment what is its charge, what is its area, and its potential. So this can be computed in any of such package, Gaussian, ADL, So this is a summary how the calculations are done. This is the, let's say, the water molecule with hydrogen positives and oxygen negative. It is placed in a dielectric constant, infinite dielectric constant. So this is the solvent accessible area, molecule placed in conductor. Then what it does is molecule will pull charge from the conductor to the surface. Now you see the oxygen atom, which is negatively charged, is having positively charged, positive spinning charges on top of it. While hydrogen, which is positively charged, is having negative charge. So we will see the reverse behavior in the Cosmo file. The Cosmo file reports the spinning charges. So then once the spinning charge is developed, then we solve it by that expression. Just now we have shown it. Just 3 terms. So this is the keyword. So this already is for benzene molecule. So this is a benzene molecule. So you have one job here. You insert the Z matrix, charge multiplicity. Then after this job is complete, you go to this job. So this job, I've used this DFT BBP 86, basis set SBP, DGA1 is like long range direction. Then this SCF, this tells us type means the convergence criteria. Now this is the important keyword. I am instructing Gaussian to do a Cosmo RS routine. Guess, read, and checkpoint means it will read from the previous file. Then you have the user, create a space. This is again the charge and the multiplicity. And then final output will be a file of benzene.cosmo with .cosmo extension. So I'll just show you what the file looks like. So when you do this, so you will have acetone, water, and toluene, for example, here. See the red ones. So for example, acetone, the Gaussian will have 739 segments. Water will have 292 segments and toluene have 1053 segments. Colors, surfaces colored by spinning charge density, blue have negative spinning values. So blue has negative spinning, which is true because these are the 2 hydrogen atoms. Green regions are neutral. So it is either negative, either positive, somewhere very close to 0. So it is green here in the case of toluene. And red regions are positive values. Red regions are positive. So oxygen has positive values. Here again, oxygen has positive values. Okay. So this is some yellow. Yellow is somewhere in between green. It is close to green. So it is close to 0. Very close to 0. Plus minus 0. So it is neither negative, neither positive, somewhere in between. So this is the Cosmo file it will be generated. Subroutine. So now you see, this is a factor. This is NPS. So number of segments, 906 segments. So for the entire molecule, it has broken all the atoms in 906 segments. That's what it says. The area of the cavity, volume of the cavity. What is the area of the cavity? It's what area you require to insert this particular benzene. In this case, it is, I think, yeah, it's benzene. So what is the area I require and volume I require to insert a particular solute? Okay, so these are the atom number 1 to 12. So atom numbers XYZ coordinates are there. Their atomic element number is there. The radius are there. The area, the total area of each atom. Total area for each type of atom will remain the same. It is 14, 14, 14. And what is the charge on each atom? The Cosmo charge. Okay, so this Cosmo charge is all this is carbon atom. So on this carbon atom of benzene, it has a charge of this much, and corresponding area is this much. Now, out of this, each of this particular surface area this is further broken up into number of segments. For example, if you go down, if you see there is some segment information. So N here is segment number. So this is the first segment. The first segment belongs to number 10 atom. Number 10 atom is which one? This hydrogen atom. And this segment has a XYZ coordinate given by this, and this. And on this segment, this amount of charge is there. And this particular segment has the area of this. So this charge by area, if you divide these two columns, is the screening charge density. Charge by area. Okay. So if you divide this by this, you get this. And this is the potential. So for example, so this will go on, it's a big file. I'm not showing the intermediate point. So it will go from 1 to 906 because we have 906 segments. So all these 906 segments are available here. For example, the last one, this is the atom 1. Atom 1 is which one? This atom. This atom is carbon atom. So this carbon atom, XYZ coordinates are given, charge is given, area is given, charge per unit area is given. So if you see it has a negative potential as compared to hydrogen. So this you will be finding out. So I'll not go into sigma profiles. Maybe we can just instruct and show how to make the Cosmo file. So just follow these two steps. Any question first? Then any questions? Yes. Just to avoid biasness, because if you put as a dynamic constant, it will be more biased towards, let's say, non-polar substance or towards polar substance. What is the value of dielectric is? That is a very difficult choice to make. That's why PCM models are limited. So once you make it a dielectric constant to be infinite, and then you use that scaling factor, you can easily then get this segment. My PCM model will only give you the total delta G. It won't give you information regarding these different segments. That is another thing, because this is we require to obtain for the real solid, the SAC-based calculation for activity coefficient. So if you want to do this calculation, you can do it. So you have to first, one of the command is this. Then what it will do is it will take up the Z matrix from this particular instruction, and then in this second part, it will conduct the Cosmo calculation using SCRF is equal to Cosmos. Okay, so can we show it here? We can show it here. You can do it for ethanol.
Yes, sir. Please make a ethanol structure in your Cosmo.
Ethanol structure you make. Maybe they can see here that maybe you can make the ethanol structure. Yeah.
Open the Cosmo and draw the ethanol structure. Yes. No.
So now you must be knowing how to make the structure in question. And the board spoke on. Ethanol. It's a very small molecule. Not much.
Now optimize this.
Just optimize this. Any drawer, it will be very quick because see here in my because I did this work earlier. There I have to specify explicit charge and something. But now, your charge is 0. Spin is singlet. Singlet means that takes care of the number of unpaired electrons plus 1. So, okay.
Everyone read to this level. Use your DFT and B3 lib 631G as a method. Write that name.
Job title you give. A simple optimization with ethanol optimization.
In job type, it should be optimized and not the energy, right? And in method section, it should be 631G, DFT, B3 lib and 631G. And write ethanol for the title for the molecule, right? Now submit this job.
Submit this job.
Everyone submitted.
Concept is the same.
Any folder.
No.
Yeah. By default input file, it will generate the log file.
So it has finished. Which means whenever this port comes,
Imagine
it means
complete.
all those 4 conditions is satisfied. Normal termination.
Anyone get this? Okay, now click to yes and open its log file, not the CHK one. Open the log file. So it should be ethanol.log, right? Everyone got that optimized log file?
So this is the optimized structure. Normal optimization. We have not come to the customer.
So after this, save again this file as opt ethanol and make sure you should uncheck that right Cartesian. So it will save the file in the Z matrix coordinate.
Yes, uncheck the right cards.
Yeah, right Cartesian should be unchecked and save this. It is saved as GZR file. So right opt ethanol to get not confused with the original ethanol.gzr. Yeah, now save this file.
Default file type.
Hmm?
File type default.
Yeah, default. Save this file. Now in the Windows search, write the Gaussian, not the Gauss view, and open that Gauss time.
They have to open
Gaussian. Gauss 9.
Gauss 9.
You got the optimized log file. Oh, you have some error. Whether you have made the
केवल आया तेरे को मस्त ये लोग का सॉन्ग एक फाइनल final coordinates or the optimized something like that. Existing now. Okay.
CRF means the reaction from what reaction you are expecting.
Everyone said that optimize log file into the Z coordinate by unchecking that earlier I have mentioned. Now open that Gauss 9. File, save. This type of is not okay. Everyone open that Gaussian 9.
Open question 9.
So after opening that Gaussian, open file, that opt ethanol that we already said in save in the diagrammatic format, right? Open that file. It is saved in the diagrammatic coordinate.
Those who have unchecked the Cartesian, they will get this file. मेरा वाला उसमें नहीं होगा।
वो कॉपी वॉइस में कॉपी करना है थोड़ा।
अच्छा वो नहीं। अच्छा ठीक है उसमें किया चेक किया।
So everyone open this file. Everyone open. Please raise your hand. Write this command percentage m equal to 100 mw and paste here. In that percentage checkpoint just above paste this command. percentage M.
It is just to.
Just above it. Then
I don't know, people are not able to see it from back.
then in the root section, just write this one. Root section, write the as it is.
Oh,
In Gaussian you cannot do.
नहीं आप नोट
Okay, okay.
उसमें जो आपका स्क्रीन शेयर कर लो
So in root section, write this S capital P BVP 86 slash SBP. Make sure the slash and the space carefully.
By now you must be knowing all the. You don't just write because he's saying. If you know what you are typing. BBP क्या होता है?
There is no space between slash and S, right? There is no space between slash and S.
That is on the right hand side. SVP is the business set along with that DGA one to the method set. Because of long set. DGA one.
इसमें कोई केस का like the case like lower case upper case and
In the percentage section, you just write, you earlier mentioned only write percentage and keep that percentage and it is.
SCF type means the converter's criteria is type. That sometimes you will not get any answer. You can also just type. There are many other options also you can use.
One of the concept, but lower than the business.
Split balance. This is which had now the basis. This is saying we are combining the acting
In that coordinates where the molecule specification is there, from here 1 to something there, you should delete this lower part. Yeah. That's already come from the Z coordinate. If you load that Z coordinates, it will show the. Just place that. Okay.
Suppose the absence of because underlying
Yes. Yeah. That part. Make sure you delete that lower part. Okay. हमने और कनेक्टिविटी हटा दिया ना हाँ now go to the additional steps. Go to the additional steps.
on the right hand side, top part, click on add.
Yeah, it is the UI error. So you go first option and add steps. Actually, that earlier one I perform one calculation. It is a next calculation. So that is why additional step which is there.
Two set of calculation. Two parts. Both parts I am putting in one particular. Both parts I am turning in one file.
Like sir has mentioned that earlier part, this we already have done, right? Now we are opening in the additional step. So that time this text means root section we have to put this. I will give you in large font.
Because this link one means the output of that file is linked with this command. That's what it means.
Okay.
So your additional step. No need to add the main link.
So in that section, only root section you put that command. I will write here in this notepad. In that after additional step. You have one additional step. In that one additional step, only change that root section.
Empty रहता है ना वो जैसे कुछ नहीं section that
In root steps. Here. Here you should. That part in the second.
Same. Cosmo is different. SCR is
Space
reaction field. SCR. So there are many options in SCR. You want to do a same calculation is not for CM. So it will do something like this. So this option people have to find in the project Q1.
Everyone done this code in the second box section. In the heading section, we have complete the root section. I hope in everyone write this in root section, right? Which one? After additional step in the root section, you must write this code. You could check that everyone has done. Everyone done that? So after this, in the molecule specification section, just write one enter, then write ethanol. In that molecular specification, just write ethanol dot Cosmo. Enter, you write that ethanol dot Cosmo.
After enter, so वहाँ पे
In
नीचे
the
वाला section में
why you get that done?
नहीं वहाँ पे नहीं था नीचे ये स्पेस में एक वहाँ पे सीक्वेंस होगा
In that molecule specification, you will put one enter and write Cosmo dot ethanol dot Cosmo. After this, you put OK, and then here run, and save in the same folder. It will ask in the Gaussian 09. Don't change the folder, and save with the same name. So it will start running. So you can see it is showing process. Yeah, I will repeat. If you take that process is completed, then it's done. But completed यहाँ पे Yes. So after optimization, go to that C directory and Gaussian 9. In C directory, Gaussian 9 and scratch folder. Where you will find a ethanol
हाँ उसके बाद ही करो वो लास्ट वाला स्टेप ही तो है उसको दिखाना है कंट्रोल प्लॉट्स अच्छा जो यहाँ पर ओपन करेंगे हाँ मेरा
Got that, Cosmo? Okay. So
this is a visualization software. आइए उधर यहाँ पे होगा सी ड्राइव में होगा सी ड्राइव में फ्लैश डायरेक्टरी में
वो
बाहर है क्या
three there.
हाँ
We can provide this one.
हाँ हाँ free है। क्यों नहीं आ रही? वो इंस्टॉल करना पड़ेगा अरे इंस्टॉल करना पड़ेगा। हाँ now so इसमें ये भी so this is the confirm so red ones are positive here.
So that software will provide you. That,
So red ones are positive and that belongs to which one? Oxygen. Only one coming a negative that is oxygen positive. Blue ones are negative. Negative are of the hydrogen. This hydrogen atom is connected to OH. Positive side. So it will be negative on the outside. So the remaining it is green. It means all of it is green. It means what? It is somewhere close to zero. Neither positive nor negative. So you can break this also in terms of this. So these are the different, the way the calculation was done. Different segments it has created, calculated.
It is bringing it into pentagonal structures and then doing the calculation.
Yes, yes. So this was and ये क्या है? ये क्या है? वो यहाँ आया हुआ है। So here you are seeing a continuous surface, but the individual segments, what you have got is all stored here. So all this segment information, so suppose these are all different segments. So there are how many segments you have got to find?
you can open this in the notepad.
635. So there are 635 segments created. So see here, it is 635 segments. And the total area on which this particular solute was inserted was this much, 321, the cavity area. And this is the cavity volume. The volume of this entire figure that you just saw. So now if you see, it will go, these are all the 1 to 9 atoms for phenol. And the corresponding so these are the radius of those atoms. So you have only this oxygen atom 8 here, and this corresponding area. So the total area is, if you add up all this area, that will give the atomic area, basically, not the surface area. Surface area is different. Surface area consisting of the union of spheres. So that surface area is here given. Here is the surface area 320. This 321 area is not equal to sum of this. It's different. And in each atom, a total charge is defined. And this particular charge is then broken into number of small things. And that individual segment information is given below. Here. So this is what you can say the cavity formation term. How much energy I require to, I require to insert the volume into the contact. This is the energy. So it is in atomic unit, you have to convert to per mole. Then you see these are all keywords given. N is number of segment, atom, position, charge, area, potential. And see this, then this starts. So you have atom one, number one segment belonging to fourth atom of the series with their positions, their charge. So negative means it is likely to come from which atom? From the hydrogen atom. Okay. So these are all negative. Now see these charges will become from negative to positive. So somewhere it will just break and become positive. See this positive, it starts positive. So these numbers, if you see here, these numbers, it is very close to zero. So it represents the green region. It represents the green region, close to zero. So it is a non-polar region basically. So this will go till 635, this particular. So actually, I have few slides after this. If you just give me 5 minutes, I will explain what to do with these segments. So much information. Suppose if you have bigger molecule, suppose you have 30 atoms, this is only common 9 atoms, 30 atoms, the number of segments. What will you do with that? You cannot do with that. What we do is we put those charges in terms of bins. Bins you understand in the first lecture. Bins in next of histograms. So okay, from this to this value, I will put all the segments. From this to this value, I will pick and choose all the segments, put it here. So that is what exactly is called the sigma profile. Presentation. Okay. You have done this, now you understand. So this is what screening charge density is quantified using a histogram known as sigma profile. Sigma profile means a normalized profile where these I represents the segment information. Particular segment has the area AI divided by the total area of all the segments summed together. Okay, so it means for an individual compound it's very easy, but for a mixture it will be you have to multiply with the mole fraction. So if you have three different components, execute a Cosmo file for all the three components separately, then multiply their profile. Then you multiply the product of their profile with their mole fractions. So 0.2. So therefore, ethanol water. So you have to do a Cosmo file for ethanol, Cosmo file for water. Suppose 30% ethanol and 70% water. So 0.3 in the profile of this plus 0.7 in the profile of this, and add up the corresponding areas like this will be the sigma profile of the mixture. So this is what it looks like. So what Lamb did was he said all the segment charges will lie between this to this. So this value sigma screening charge density is nothing but charge by area, Q by A. So fourth column by fifth column. Fourth column is the charge, fifth column is the corresponding area. So this is the chart. So now what I do, I will write a MATLAB program or any program. I will collect all those values, the areas of the respective segments in the bin. Let's say I make a bin of 0.025 to 0.024. So in that particular file, I will use some string character that okay, that particular segment, which of the segments has a charge between these two groups. Then read its corresponding area, add them up and put that here in a histogram. Like that, you keep different 0.024, 23, 22, like that, keep on making bins and add up the areas. If you put those areas, you will get this type of profile. So what does this profile mean? So whatever number of segments you have, you can bring that all into this profile. You don't worry up to number of segments. It is all coming into this histogram. So I've taken three components: acetone, water, hexane. Hexane is, is non-polar. Water is having a very high boiling point, and acetone is somewhere between water and hexane. So it means in green, if you see hexane, you don't have any charges which are extremely positive, extremely negative, or extremely positive. So most of the charges are close to zero. They're all similar charges. So we give a cutoff. The cutoff is provided by the Andreas clamp. It says charge segments which are to the left of this cutoff and to the right of this cutoff will have more than high interaction. That is, they will be having higher boiling point. They are closely packed. So that is true because you see water, it has a significant part of its profile, the right of the left of this part and to the right of this part. It means that is the reason they have hydrogen bonds between themselves. Have a high boiling point. While hexane doesn't have any hydrogen bonding between themselves because it does not have any profile lying to the right of this side or left of to this side. It's all zero. Acetone is somewhere in between. So it means the peak you are seeing here is due to which atom? Can you tell me now? This peak? Because it is in positive in nature. It is for oxygen, the oxygen atom. Because of this oxygen atom, we say this region. So for water, these are the oxygen atoms on water, and hydrogen atom of water is due to these peaks. So we take this particular area to the right side of this cutoff as hydrogen bonding acceptor capacity. So if this particular zone can accept. So it means this particular segments can interact with these segments. These segments can interact with these segments. So these are called hydrogen bond donor region. This is called acceptor region. And the remaining area is called non-polar region. That's what it is. The entire schema profile.
So does this mean water?
Yes. Water and yes. They will have better interaction if their profiles are complementary. If two compounds profile are complementary, understand? Not exact same. They are complementary. They are not overlapping. They will have high solubility. And if it just overlaps on each other, it will have they are immiscible both the compounds. So if you see for water, it is highly symmetrical type of structures. You have profile to the right, to the left, everywhere. So that actually makes the point that why water is a high boiling solid. Boiling point is very high. And hexane has a boiling point very less, 78, right? Because they are only non-polar. Okay, this is the reason. So this particular, when you do everything normalized, it becomes a probability distribution. So not probability distribution, the distribution of the charges on the surfaces. So I am putting it all the compounds in one particular reference plane. That's what it means. So forget this. So this, as I told you, these solvation maps have to be done only once. If you do once, store it, it becomes a database. So that database is already there in many open literature. So you can take the database already from there also, the Cosmo file directly. So this has to be done only once because it's a unimolecular quantum chemical calculation, single molecule. So now after this, the subsequent portions of the model, the RS or the SAC part, which I have not discussed here, that will account for the transfer from the conductor to the actual solvent. Now the charges are developed onto the surface. You have obtained the charges by the Gaussian calculation, but do we have actually these charges? No. So now the next part of the modeling comes. What is the energy required to remove these charges to restore it to its original state? So that in that the statistical thermodynamics comes into the picture. So that I will not discuss. So overall, this is what it is. So basically, what we have started, we started with a single molecule, placed it in a conductor, charges are induced. So it becomes a Cosmo scheme. We imply or execute a Cosmo scheme. Then what you do is with this, we break them into segments. further break them and seconds, and then we represent it in this manner, sigma profile. Then we replace the interacting molecules. Overall, what we have did is, if we have 3 components, we have 3 corresponding number of segments. We have replaced the entire molecule with pairwise interacting segments. So, what is the summary? The SCF calculations has to be done only once for each component. Once these charges are obtained, then a framework has to be created so as to restore these charges when placed in an actual solvent of a known dielectric constant. This is where the derivation of chemical potentials and activity coefficients is possible. Because we as engineers, we are well known with these terms, activity coefficients. You read it in thermodynamics. So activity coefficients you can predict from unimolecular quantum mechanical calculation. That is what our objective is. Many of you must be knowing those who are from calculating background. You know NRTL model, unified, all these things. NRTL unified, they will require experimental data to regress the activity coefficient. Here, you don't require any experimental data. You are starting directly from the quantum chemistry principle. So our aim is obviously not many Cosmo files have already been created. So the repository is there. That's it. Any questions? I answer everything. That's yeah.
Is decided on the top surface charge density.
It is decided by, they have done what they did was they took the bond dissociation constants, the bond energy of bond more than 15,000 clamp here. And they found out that rigorous optimization that this particular value is got a unique parameter. So which can actually segregate the hydrogen one could you have the calculation then I will not change this particular value for some other compound. This is a unique global parameter. You will not change the system. It is not system specific. This 0.025, whatever bit that is there to stay for any kind. Okay, so that the charge. At this moment, we are just only doing it for an ionics. That part is in the RS. That is, we have written our own code. That is, we have in MATLAB. Cosmo has it. The packet itself has it at the back end. So that is normal. You can write in any programming language. How to remove the charges? So what is the energy? What is how do you write the delta G expression? I can cover that, but we take another 1.5 hours. So I don't do it here because many of you are not from chemical engineering background, right? How many are from chemical engineering background? Half. So that is where the rigorous statistical thermodynamics comes into the picture, the coding and all those things. So will that be covered in that? Which one? Upcoming one? No, I'm not covering one. Because that is purely to note some concepts of statistical thermodynamics before I cover them. And symbols, all those things. And symbols will be covered tomorrow in molecular dynamics. Okay. Okay, we'll stop here then. If any queries are there, the next 2 days on. Then I'll take a so, okay, we dispersed them today. They were all done for today's session. So this will be given, all the files will be provided. They were this can be used as an input for console as well. As well as any other like simulation software, I can use this to generate the file. Yes. But I'll have to like this particular sigma profile.